So next to the what Fisher, we have what the Newman projection. It is also the conversion of molecule from 3D to what the 2D. Similar to that of your Fisher projection, we have rules are there. To by using that rule now, we are going to discuss this Newman's projection now. The first rule for the Newman projection is if we have to see the molecule around the carbon-carbon bond, that means just one behind other. Suppose one carbon is a front carbon, a second carbon is just behind to that front carbon. Okay, so one back to other. So basically, we have to see the molecule along carbon-carbon along this carbon-carbon bond. Okay, that means whenever observer see the molecule, it only that means your front carbon is only what the visible, or the front carbon should be what the is nearer, while the back carbon is away from the observer now. So the second rule is what? Carbon which is nearer to observer, which is called front carbon. So front carbon means what? Front carbon means the carbon which is nearer to observer. Nearer to observer, this is called the front carbon. And which is back carbon now? Back carbon means it is away from the observer now. And generally what happened here? Front carbon is denoted by a dot. Front carbon is denoted by dot, and back carbon is denoted by the circle. Back carbon is denoted by the circle now. And each and every line should be keep as a, or we have to maintain the angle as a 120. So keep all the three lines, keep all three lines or three bonds 120 angle of separation to each other. And you know that as in all conformation analysis, so Newman see the best conformation analysis. That is, it is the best for conformational analysis. Best for conformational analysis. So are you getting the rules? First of all, what we have to see the molecule along the carbon-carbon bond. Example, front carbon. Suppose I have ethane now. I want to draw the structures of ethane now. CH3 single bond CH. Now, how many carbon in this molecule? 2 carbon. So your front carbon should be as a dot. This is now dot now. Okay, this is the front carbon. You know that on front carbon, how many bonds are there? 3 hydrogen and 1 carbon. 3 hydrogen and 1 carbon. Okay, so these 3 hydrogen, are separated by which angle? 120. Okay, 120. That means this is all the hydrogen. Suppose example, these are green hydrogen. Okay, this is hydrogen, this is hydrogen, this is hydrogen. This is about the front carbon. Now what about the back carbon now? The back carbon is as a circle. Example, circle. I'm going to just make a circle at here now. This is my back carbon. And on a back carbon, okay, there are 3 hydrogens are there. Okay, and which I shown in the next color. Example, this one. This one. And these 3 hydrogens are look like this one. They are also separated by 120. Okay, this type of what representation is called as a Newman presentation. Which is your front carbon now? Dot as a front carbon, and circle as a back carbon. Back carbon. Circle is a back carbon. Okay, that means we have to see the molecule along with the carbon-carbon bond. That means that behind the dot there is a carbon. And that's why we need to show the carbon-carbon bond here. Okay, this is a simple task in presentation now. Now look at the angle between these molecules now. What are the angles now? Okay, example अगर हमने लिया है, so these angle first 3 hydrogen are separated by 120, and last 3 hydrogen also they are separated by 120. Okay, first 3 separated by 120 and last 3 are also separated by 120. But if you see carefully, the relationship between first and back, any 2 hydrogens or angles are different. They are not 120, or they are not like that. Okay, example, if you want to show the angle between this and this one. Example, the angle between this, it should be what the 60 degree. Suppose this green and this green want to find out the angle must be what the near about, it's more than, or it is about the 60 now. And if you want to see the angle between these 2 hydrogen which are opposite exactly, they are called the 180. So we'll discuss the angle and how this will be proceed now. So for any molecule, we can make this type of the presentation. There should be a 2 carbon is needed now. How many carbons are needed for this presentation?
2 carbons.
Here are 2 carbons should be there to explain the Newman prediction. Okay. So I can also draw the same structure in a different format. Example, this is my front carbon, and there are 3 substituents are there on the front carbon, which I mentioned in the green color. Look, you can also make this. Okay, no question at all, or you can make simply like this one now. And these are my 3 hydrogen, which are separated by 120. Second one, the circle which I made here, this is the back carbon. This is what? Back carbon. And now these circle hydrogen can be arranged in this fashion also. I just rotate that back carbon now. I just rotate that back carbon and I will get this one. So here from we can also conclude that okay, this red this dot is nothing but different carbon, circle is a back carbon. So that means whenever you do the conformation analysis, that means rotation of carbon-carbon bond. If you rotate that carbon-carbon bond, one of the carbon along with the 3 hydrogens are in constant. Only what the substituents which are adjacent to the next carbon or the front carbon, anyone, you can choose anyone, okay, for the rotation now. They undergo the rotation. And you know that this and this both are different structures now. They are structurally they are different. Because here the angle between these two are theta is equal to 0. That this structure is called as a eclipsed structure. This is called as a eclipsed. So whenever these 2 hydrogens are 60-degree separation, that type of the relationship is called as a gauge. And whenever these hydrogens are separated by 180, then these 2 hydrogens are called as a staggered. So there are 3 types of the relationship between these substituents now particularly. And you know that Fisher is the eclipsed conformation. Fisher is the what? Eclipsed conformation. Now that means you can easily convert into the Fisher now. What is Fisher now? Here, this is what Fisher now. This hydrogen, 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 and hydrogen. That means this structure is represented like this fashion. Understood? Because in the last lecture we have discussed that Fisher is the eclipsed.
Eclipsed.
Okay. You can also convert into the wedge now. What is wedge now? So we have to make a bond like this. So in that, this is the one substituent. You can also convert into the wedge now. Example that like this. This is my carbon-carbon single bond. Look at the molecule. This one. Okay. So you have now already we have discussed the first 2 now. Wedge, Fisher, and now it's Newman. That means single molecule can show the all the 3. So we'll discuss some example how the interconversion of the molecule now particular. Suppose I have the tri substituted molecules on this. Or you can take the example as suppose this is my circle, dot and circle. Okay, this one. And I will make the changes here. So example this one now. Okay. And here first we'll take the eclipse confirmation. It will be easier. 1, 2, and 3. And give the names to that particular substance. Suppose example this is my A. This is example my B. This is example my C now. A, B, C are there. Now we have the next type is what the next naming is what the D, then what E, and this is F. Now just rotate that molecule via 120 degree. What happened now? Always remember rotation means it is a carbon-carbon bond rotation. That means we have to fix the one carbon with the 3 substituents and just rotate the. Generally, what front carbon is constant and back carbon is get rotated. Now, what happened if you rotate that molecule via not 60? I'm talking about the 120 now. If I rotate via the 60, what happened now? This B is going to take this position.
Yes, beech mein aa jayega.
And this will going to this position now. But I am going to rotate via 120 now. That means Okay, that means this is my circle and this is my dot now. Okay, these are the three my constant substituent, which is named as a F, D, E. Okay, D, E, F. And now I am going to change their position. This is my A. This is A. Okay, this is what C and this is what B now. Again, I rotate that molecule via 120. What happened? What happened? What the 120 now? Yes. So these are F. This is E. This is what the D now. And here, this is what A. This is what C. This is what B now. And what about the last one? If I rotate that molecule, so 120, 120, and again 120, right? You get the original one. So now take this, right? Take this molecule and just rotate via what 60 degree. So what happened now? 60 degree rotation means you get the 60 degree rotation. These are what F, E, and this is D now. So 60 degree rotation leads to this molecule. Got it? This is C, this is B, and this is A now. Okay. Now remember the relationship between the any two substituents, front and back. Okay. The relationship between the front carbon substituent and back carbon substituents are if theta is equal to 0 degree, then such a conformation, such kind of the molecule orientation are called as the eclipse. Eclipse means just one behind other. If the theta is equal to what the 60 degree, then it is called as a gauche. And if the theta is equal to what 180, then it is called as a staggered. So these are the three relationship between the substituents, front and back. Okay. You can take the simple ethane molecule and do your work again, no problem at all. So take the simple ethane molecule, CH3 and CH3 now. This is my molecule example. First, that molecule is converts into the Fischer form. This is the Fischer presentation. Hydrogen, 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 and this is also hydrogen. Now that will be converts into the wedge Fischer, one can say. Okay. अब हम इसको कन्वर्ट करेंगे उसमें न्यूमन में. So Newman is make the circle, make the dot, and here these are the substituent. All are the, because Fischer is a eclipse conformation, so we have to first make the structure as a eclipse now. And then I'm going to do the rotation of 60, then 60, then 60, then 60, like that. First is 60 rotation, then next is 60, that is complete 120. Yeah, directly 120 ka karo. Okay, so do the 120 rotation 3 times, you get the original structure. Okay, or first do the 60, then another 60, that means 120, another 60 means it is 180, another 60 means 240, then 300, and then lastly what the 360. So like this we have to make the changes. Okay, and all this is called as a confirmation analysis. Okay, do your work here now also. We'll take the one more interesting example, because for that more clarification, give the numbers to that hydrogen. Example, suppose my the hydrogen numbers are, this is my H1, okay, this is my H2, and this is my H3 now. Okay, similarly this is H4 and H5 and H6, because without number you cannot distinguish, because all are the same substituents. So that's why give the number and do the all rotation. After look at the structure first at 60 and then look at the structure at the 360. So whether it is the same or different. Okay. Bifunctional molecules now. You know the bifunctional molecules are tartaric acid. So this is called mesotartaric acid. Example, this is my OH, this is my OH, and here is what CO2H. So this is called mesotartaric acid or tartaric acid simply. Meso means it should be converted into the Fischer projection. Then we can call it as a meso. Example, look at this one. This is one. This is what the OH. This is what the OH. This is CO2H, CO2H. Whenever a mirror plane of symmetry is there in the molecule, that will be called as a meso now. Okay, mirror plane between the two carbon of OH. Now that molecule is in Fischer. Fischer is going to be converts into the Newman. What is Newman now? Make a circle here. Okay, and make a dot as a front carbon and circle as a back carbon. There are three substituents on the dot first of all, and these are, suppose example, this is my OH, this is my COOH, and this is my hydrogen. These are my three substituents. Similarly, I have the back carbon. And on back carbon, so this is my OH, this is my CO2H, and this is my hydrogen. This is my meso conformation. This is meso, and this is eclipsed, because what, all the Fischer are eclipsed now. Now first to do the rotation of 60 now. What happened? So do the practice here now. Without practice, it's very difficult. Okay. This is my the three substituent should be like this fashion. Okay. So I will change that color. Okay. This is my front carbon, COH, OH, and this is H. What are the remaining three substituents now? 60. 60 means this is my hydrogen, the OH. Okay, got it? Now do the same by 60 now. What happened now? Again, there is a change in the position of the substituents. This is my circle, that is a back carbon, and this is front carbon. So here you can use the front carbon also for the rotation. Then we have to constant the back. Okay, you have to fix the back now. Okay, this is my front carbon. And what about my back carbon? This is my hydrogen, this is my OH, and this is my COH. Okay, now further I will do the same. This is what the 60-degree rotation. 60 will leads to the changes like this. This is what OH, COH, H. Next to that, here this is my COOH, this is my what H, and this is my, that means up to that we have 180 completed now. Further we have to do the same, that is what 60. What about to this? Right? Now the next one. So you will get this one. Correct? And now if we do the last one, so that last one will the final one, right? If I do this 60, so I will get the original. And now the question is that relationship between this compound. The first is eclipsed. Second, OH are on an adjacent side. That's why it is a perfect gauge conformation. It is what the gauge. This is eclipse. Then second one is a gauge. Then again eclipse. You get the eclipse now. This is what eclipse. This is example of what staggered as well as gauge. If you look the COH, it is a staggered. Or if you look the COH and OH, it is an eclipse now. Similarly, the next molecule is again eclipsed. It is with respect to the COH and OH, it is again eclipsed. But if you look the OH and COH, they are staggered. So, but same groups are opposite, so you can call as eclipse now. And lastly, what the eclipse now. So you can do this kind of what the conversation in a molecule now. But what we have to do now, just look, remember one thing. So rotation will be done on a single carbon. Okay. Now, if I take that last molecule, that is which I originally, it is same to that of original now. And can I convert that molecule onto the Fischer now? Yes. Look at this one. This eclipse is equivalent to what the meso now. Eclipse is equivalent to meso. Now this one, look at this structure. Okay. But one last. OH and COH are just below each other now, and that structure is basically is different from that original one. So from that we can discuss the molecular properties of that particular molecule. Okay, so Fischer, that's why we have to convert into the original last structure. It becomes a proper one, and there are various examples are there for this type of a presentation.